we were looking at we were looking at this. Okay, let me go back to this question. Right, we're looking at this question in our previous lecture, and I completed it, no doubt. But there are some questions from you also would like to just clarify. So just to refresh our memory, we have this example here. The case of a zigzag pipe, Y-shaped pipe. Because in industry, not all pipes are straight. Some pipes are zigzag, some are zigzag at a certain angle. Okay? Some go to T-joints. And so different types of pipe connection. And later on today, we'll study pipe network. But not just one pipe, but many pipes forming a network. Okay? How do we go about calculating certain values? So we had, last week we had this pipe here, and we had a pump and a growth bar. We know what a growth bar basically is now. You have to control shut off the bar, the flow of the water, or you control the flow rate by just half closing it or just sliding closing. Okay? And there are two elbows here, one there and one there. Okay? And so the question goes like this. Here, this pump connected to a 4.25 meter diameter pipe, okay, and has an overall length of 50, okay, and it operates a flow bar at 290 degrees bend. Okay, and we have given this performance relationship between the head and the flow rate. Okay? The head and the flow rate for the pump. Okay? And so for the delta T, of course, the pressure drop at QC volumetric flow rate means the flow, the quantity of flow per second through the pipe. And rho is the standard density, of course. And to have calculated the average velocity, no problem. With that all is estimate the maximum flow rate to the pipe, draw the pump characteristic curve and show operating point. So what is the operating point? I told the operating point. Here, a typical pump characteristic. The typical pump characteristic curve is always of this shape. We have the head and the flow rate. The typical pump characteristic is always of this shape. Right? So it is different for each pump. Different for each pump. So pump 1 may have this characteristic curve. Pump 2 may have a slightly different type. So pump 2 may have, for example, pump 2 may have, for example, a different characteristic. Okay, this will be pump 2, another pump. And then you get another pump 3, for example. Okay, it's all different. So, a different pump. So different pumps, they are very individual, just like names. Names. Okay? Depending on the pump design. And this is the system curve. This is the pipe network system curve. Okay? In other words, if the flow rate increases in the piping system, the head required will go up. Okay? The head required, or in other words, there's a great deal of pressure loss. There's a great deal of pressure loss as the flow rate increases in the piping system. This is the piping system curve. It's a piping system curve. So in other words, if you have a pump in a pipe, and the pump is pumping flow at a certain flow rate, and you have a pipe system that is following this characteristic curve. So when you size that pump, you want to make sure that you utilize this pump at the optimum point, not undersizing it. If undersized, you will not be able to produce the flow from point A to point B. Okay, if it's undersized. If it's oversized, then of course you're paying for something that, over extra what is required. So you want to operate at the ideal point. So the ideal point where you actually maximize the potential of the pump, or to be this the ideal point here, called the operating point, where the pump characteristic curve and this type system relative curve intersect. So that is the ideal point. Alright, hope that's clear. So we went on to look at the question, we have calculated the amount of pressure drop at the operating point. We can also we have calculated the amount of pressure drop at the operating point. We have also calculated the power of the pump at the operating point. Okay? At the operating point. So what is this power of the pump? Power of the pump basically is the flow that it produces times the delta P across the pump. Okay? Times delta P. Or delta P that the pump can produce. So, and also bear in mind, of course, we have this K here. We know what K is now. K is the loss coefficient. So, just getting the flow from point A to point B, there is a pressure drop. It is we call it the major loss. Major loss. Now, if you were to put a valve in between, it's like optical. If the flow has to be clear. Okay? And there will be more pressure drop across the valve. So that is the minor loss. Minor loss. And if you were to bend the pipe to one elbow, there will be pressure loss across the elbow again. And that is part of the minor loss. So valves, fittings, elbows, joints, they cause minor losses. Okay? For a straight pipe, or just even a curved pipe, just along the pipe itself, that pressure loss along the pipe length itself is the major loss. So we have major loss and minor loss. So I hope that is clear. Huh? Okay, so today we will move on. Here we look at complex pipeline system. Complex pipeline system.